Hello, everyone. Welcome back. Hope you all had a good lunch. Our next session is with Development Seed, an international organization headquartered in Lisbon and Washington, D.C. Development Seed is dedicated to addressing complex social and environmental challenges by harnessing the power of open data and cutting edge technology. Their impact tools have been trusted by leading global institutions such as NASA, the World Bank, and the Nature, and have played a significant role in tracking natural disasters, managing refuge crisis, and analyzing election dynamics. Today, to represent, we have with us Mr. Soumya and Tarashish from Development Seed. Mr. Soumya works as an ML engineer at Development Seed, specializing in Earth observation, EO foundation models, and large language model workflows from geospatial interfaces. His work advances the integration of AI and technologies. Now, Mr. Tarashish is a generalist software engineer, passionate about building software that solves real-world problems. He is currently a cloud engineer at Development Seed. He develops tools and infrastructure to support scientific research and creates AI solutions for geospatial workflows. So it is really an honor and privilege to have you both here. I welcome Development Seed team to come forward and address the gathering. Share the keynote.
Hello. Should we give a minute for people to settle down a bit before we start, or we have everyone in the room? We can start? We can start? Okay, cool. Hey, everyone. So I'm Samya. I'm here with my colleague, Tara. We are from Development Seed. So DevSeed is a nonprofit that's based in DC and Lisbon, and we work a lot with open data, open platforms. So some of the organizations we work with is NASA, Google, WRI, Nature Conservancy, to name a few. Before we start the session today, we'd love to do a poll. If people can just scan this QR code and answer a few questions. I'm not sure. Sir? So cool. Okay. So if everyone can like quickly scan this QR code and answer a few questions, that would help us to better like align this talk towards the audience today. Scan କରୁଛନ୍ତି. Okay. Cool. Okay. So this is me. So I'm Soumya. I work as a machine learning engineer at DevSeed. I mostly work with NASA on their foundational model. So there's Prithvi. I'm not sure if you guys have heard of it. So Prithvi and Clay are some of the models that I worked on. Lately, I'm working with large language models. So we're building mapping interface for WRI and Google. And he's Tara. So he works with NASA as well on its IEEE platform. He also contributes to Jupyter. If you are using Jupyter in any of your work, that's something that he contributes to. And before this, he was like heading engineering at OCCRP. I now hand it over to Tara, and he'll start the tutorial on cloud native data formats, and then I'll cover foundational models. I guess.
Hey everyone, I'm Tashish. No more introductions. I guess we have had enough of those. I'll just jump right in. So my goal is to just get you a sense of what cloud native data is to get us all onto the same page before we dive into foundational models and yeah, the meat of the tutorial. So we have a Google Colab notebook here. This is linked from the same web page that we have from the for the tutorial, and you can come close. Okay, this one. You can follow along, but I think it's fine. Like the notebook is there if you want to do this later, and you can just follow on the screen for now if you want to. So first, let's get started here with setting up some of the libraries that we'll use in this notebook. I already have those set up in this environment. And now we can get started. So yeah, I can share the QR code again. Yeah. The slides are also linked from the web page we have, so you can access it from there. So yeah, let's do a quick introduction to cloud native data formats and stack. So in general, when we're working with satellite data, geospatial data, there are lots of different formats. There are rasters, vectors, point clouds, and generally these are big files. And if you want to work with these data files, you have to download the entire file to your system, and you open those files in like QGIS or whatever your favorite geospatial tooling tool stack is. And then perhaps you only need a small portion of that data for your analysis. So that basically has a lot of inefficiencies because only to analyze a small subset of the data, you're essentially downloading the whole file. So the main aim of cloud native data formats is to address that inefficiency. So the key characteristics of a cloud native data format is that they support parallel reads from multiple processes, and they support the ability to request only a certain range of that data file that you require for your analysis without downloading the entire file. Cloud native data formats also have a way to specify the metadata separately so that you can only ask for the metadata without downloading the whole data file. And internally, these cloud native files are stored as chunks or tiles, so you can selectively pick which portion of the data file you want. I think this one. Is that visible? Probably not. Okay, let me just do like a new slide. Oh yeah, I can do a duplicate, right? Duplicate slide. Yeah, just calculate. Oh no. Yeah. Okay, this is the link of the website. Should I zoom in a bit? I don't know. Maybe, no. Mhm. Yeah. Is that better? Okay. All right. So yeah, so cloud native data formats basically let you download only chunks of the file of the geospatial file you're interested in without downloading the whole file. How do they do this? They use something called HTTP range requests. These requests basically let you define a range of bytes that you're interested in. So it'll only download those bytes from a remote file. Like I said, we have different types of geospatial data formats, right? So we have vectors, so lines, shapes, polygons. We have point clouds or points. We have raster data. So for all these, we have different types of cloud optimized data formats. For vector data, we have flat geobuf and geoparquet. For points, we have cloud optimized point cloud. For raster, we have COGS, cloud optimized geotips, and ZAR. So today we're going to talk about COGS and ZAR a bit, and we'll also talk about Stack, which is a data standard that we use for organizing these files. So yeah, moving on to Stack. Stack stands for Spatiotemporal Asset Catalog. So here's a problem that we're trying to solve here, right? So there are lots of producers of geospatial data in the world. They all store their data in different ways. So you have a problem, you want to explore the data from a certain time frame, from a certain geographical area, you have an area of interest in mind. Now you go onto the internet, you look at what's available there, and all these providers have their data in like slightly different format, scattered all over the place. So there's no standard way to access this data and search through it. So the point of Stack is to fix this problem. So we have a standard set of formats that we use, or standard set of standards we use to describe these geospatial data sets. So a stack catalog is basically a grouping of collections, and collections are a grouping of items. So items you can think of as individual satellite images, right? So collections are a grouping of those. And then a catalog is basically a grouping of collections. So we have, so Stack is not something new. This is pretty widely adopted by the geospatial community. So now, I think the biggest one is Planetary Computer by Microsoft. And then NASA also has lots of internal Stack catalogs. Element 84 runs a huge Stack catalog on AWS. And so this is a very widely adopted standard for sharing geospatial data sets. And we have tools in the ecosystem to list all these catalogs. We have tools like Stack Browser that can help people access and browse through these catalogs. And these catalogs basically have data from all kinds of providers. So on planetary computer, you have data from Sentinel, you have data from the Planet Labs satellites, you have data from open aerial maps, I think. And so there are lots of different types of catalogs, all laid out in a standard pattern. So you can access these data sets through the same libraries, same set of software tools. So yeah, here's a quick look at the how a stack catalog looks. Like you have IDs, you have types, description. Similarly for collections, items, you have like a fixed set of fields, and this is all extendable through stack extensions. Very well laid out standard, and this is developed by the community, not by any specific organization. So with that in mind, let's look at some specific data formats that we're going to talk about. First is cloud optimized geotips. So geotips are basically your standard TIFF files with some geometric metadata. But again, if you want to download, if you want to do any kind of analysis on a standard geotiff, you have to download the whole file to your computer before you can do anything. Cloud optimized geotiff add a twist to that for efficiency by doing internal tiling so that the files are tiled internally to store data in internal tiles that are tied to specific AOIs. So if you want data for a small AOI, you can ask for tiles that cover that AOI only without having to download the entire file. So internally, they store metadata in a block, and then you have these tiles that store the raw data, and then overviews that are like the view at other progressive zoom levels. So if you want the data for a particular region, for a particular zoom level, you can basically ask for the related tile and then get the overview from there without downloading this whole thing, this whole file. Yeah, sure. Uh-huh. Yeah. Yeah. Yeah, so planetary computer is basically Microsoft's equivalent to Google Earth Engine. So they have a lot of the same data in stack format. Also, I think from what we know, there is some ongoing effort to get Google Earth Engine to also they are moving towards that. No, they don't. Currently, they don't. So they are currently. So Google Earth Engine is not on stack right now. Okay. So yeah, I know that there are efforts to move in that direction, but I don't know if the entire catalog is on stack. But if it is, then that's great. Yeah, and I think for the bigger data sets, most of the Sentinel-2 and all that, most of those data sets are available on Planetary Computer and on the AWS stack catalog. I think so, yeah.
So Stack was built as a standard to counter Google approach. So it started as a community initiative to counter Google approach. And Microsoft came up with they said, okay, we'll build planted computer, which will act as a driver into the world. So, and they built also the team different planted computer. Microsoft is fine. There's no team now that's building planted computer. They're just maintaining the data catalog. So Google Earth Engine has a data catalog, and then there is a compute infrastructure that allows you to access the data. Planetary Computer was that, like they had a data catalog and they used to give free compute instances for researchers, for everyone actually to go query the data, build models on it. But that's gone now, right? So Microsoft couldn't sustain and they couldn't support. Tomorrow Google can say the same thing, like, oh, we are not able to like pay for your compute instances. So you either have a subscription model or you pay $10 a month. So Stack is kind of like a community initiative, and it builds on the catalog. It builds on like how you make data access efficient, how do you make data processing efficient and cheap for people, so that they don't have like a single option to pick from. They have like an open option as well.
Yeah.
Yeah.
Yeah. Mm-hmm. Yeah, I think for now, planetary computer is what we use. But as you see, like these are like private companies can go away anytime, right? So the data catalogs for planetary computer are still there. The same data for like most common data sets, it's still available on the AWS stack catalog. Yeah, I think for now we rely on those two mostly. And the hope with Stack is that we standardize this across the industry so that more people can basically support this, right? So there's more redundancy across organizations so that even when one catalog shuts down, there are two that can provide that service to the community. And both of them are free to use right now, but they don't have any compute, right? This is only the data. So the compute. Yeah, that's the beauty about Stack, right? So the same data is also available on other platform. If that same data set, same collection is available on another Stack provider, Stack catalog. So you can basically plug that URL into this tutorial and everything works as is, right? So that's the beauty of it. So even if one catalog shuts down, you can quickly just switch to another catalog that has the same collection, and all of your stuff just works. So yeah, that's, I think the point of standardization is that, like, you don't rely on one big company to kind of provide you free assets. Right. So where were we? So we're talking about COGS. Now let's talk about another similar data format called ZAR. So COGS are, so the concept is similar, right? So ZAR will provide internal chunking for your data. It will provide a way to store metadata. It will provide a way to access data in parallel, all this data in object storage, so S3 and similar services. So it's flat files. You can request the data from as many parallel workers that you want to. But ZAR is more suited towards multi-dimensional data cubes than COX. And internally, as you can see, it will basically store the data in chunks and then compresses those chunks. So the size of the data is a lot smaller. And then when you want to retrieve only a small AOI, you can only retrieve those chunks that that intersect with the particular AOI and process those. So as a practical example, where we have an example where we'll use PyStack client to get the ERA5 data from ECMWF. ECMWF is basically the weather forecasting agency for Europe. They have been collecting this data about air temperature from 1940s to like the present year. And this covers the entire Earth. And then we have 137 levels from the surface to 80 kilometers above surface. So it has 137 levels across the entire world from 1940 to the current year. Now, all these data combined is petabytes of data. So if you want to analyze the trend in India for a particular year or a particular month, you have to basically download at least gigabytes or terabytes of data, and you have to know which files to download in that collection. So it's basically impossible for someone with just like a consumer grade computer and a normal internet connection to do. But the thing is, with Stack and all these cloud optimized data formats, we can do that now without downloading that much data. So yeah, we basically instantiate PyStack client here. We point it to Planetary Computer. Planetary Computer has a bunch of collections. We list some of those collections here. We look for ERA5 in the all the collections they have to identify the collections we are interested in. As you can see, ERA5 PDS is the collection that we're interested in. It has some summary and metadata description. We have 2 data points here, forecast and analysis. We're mostly interested in analysis in this tutorial. So yeah. Now, we are interested in data for India, so we have a bounding box here for India and date range. So we're looking at 2020, the Kharif season, so June, mid-year to end of November here. And we're only interested in the analysis. So we have this filter which says, give me only AN, which stands for analysis in this case. It queries the catalog, finds 6 items in this catalog. And then all these items have assets linked to them. So we list the assets on these items. From these assets, we are interested in air temperature above 2 meters above the ground for this tutorial. But you can see you have above 10 meter, above 100 meter, and a bunch of other assets as well, if you want to access those. So we get the link for that particular asset. We open that in Xarray. Xarray is a Python library that is used to open multi-dimensional data sets. So as you can see, this data set, when filtered down to the data 2 meter above ground level for this month for India, is 2.78 ZBs here. And yeah, it has lat long time as indexes. And then we want to, so for now, this is the whole data set. Then we filter down to only the area of interest we're interested in. So the B box around India. And that comes down to only 42 MBs. So we basically filter down the data for the whole Earth, which was 2.78 GBs, down to 42 MBs. So this, and the good thing about X-ray is that all these computation is happening on the metadata only. So you're not downloading the data just yet. So only after you have filtered down to the data you are interested in and zoomed in on these 42 MBs of data, then only once you start computing, it will download that data. So instead of downloading the whole data set, now we are only downloading 42 MBs of data, which is absolutely doable on a weak internet connection and a weak computer even. So yeah, we download that data with dataset.compute. We have the data here. We save it to a ZAR file if you want to use it for further processing later on. But yeah, once the data is there, we're computing, this data is hourly. So it's in hourly resolution. So we're resampling it to a daily resolution and then computing a mean. So now we have daily mean temperature for across India for that month, for June. It's in Kelvin, so we convert that to Celsius, and now we can just use matplotlib to plot that data on a map. This is our B-box. This is the data plotted on a map. Matplotlib also lets you do animations, which, yeah, I don't know. It's fun to look at, but I don't know how useful that is. But so yeah, we can use this func animation function that Matplotlib provides to also compute animation. Let me see if I can play this. I'm just regenerating that animation, but it's very fun to look at. Let's see if that works. Is it? Yeah. Okay, I don't know. Yeah, as you can see, his animation, it's somehow cut off, but I hope you can see that it's animating. So yeah, it's basically the point of this talk is that if you use these new data formats, cloud optimized data formats, not really new, people are already using it in real world. It lets you do more with limited resources. So even if the data is huge, as long as it's in cloud native data formats, you can use limited compute, limited network bandwidth to access and analyze data in large scale without having to spend a lot of time and compute. With that, hope that gives you enough introduction about modern geospatial formats. I'll hand it over to Soumya to talk about Earth observation models and foundational models. Thank you.
Yeah, thanks, Tara. Okay, we'll go back to slides. But before we do that, I'd like to do a quick pulse check, right? So we don't have a lot of people in this room. So we can quickly do a hand raise if that's all right for everyone. So can people tell me like how many of you are from industry here? Like a quick hand check. Like how many of you are from the industry? Just one? Okay. How many of you are from academia? Like from universities, colleges? Okay. Okay, cool. How many of you use, okay, cool, nice. How many of you use QGIS in your daily workflow? QGIS, ArcGIS, like any of the like tooling kind of things? A lot of you? Okay. How many of you program in Python or have written programs in Python? Python programs, everyone? Anyone who doesn't write program in Python? Anyone in the room who doesn't understand Python? Cool, everyone understands Python here, okay. And people who have some knowledge of machine learning. Some knowledge of machine learning? Some, okay. Some knowledge of deep learning, neural networks, CNN, transformers, some knowledge. Okay, I see a lot of people have good knowledge on this. Okay, last question. How many of you have heard of foundational models? Do you know what foundational models are? Okay, one. Okay. How many of you have heard of ChatGPT here? People, ChatGPT? Yeah. So ChatGPT is a foundational model. Okay. So we'll talk about foundational models today. But before we do that, like, I don't want people to be scattered all around the room. It makes me a little difficult to focus on. So can we have people come a bit front? Is it okay if you guys come to the front? There are a lot of empty seats. It will also be a bit more involved. Cool, yeah, let's do that. People there, like, do you want to come to the front as well? Like, it's okay. Like, we are just gonna have like a very casual discussion around foundational models. So let's do that. A bit front, like you don't have to sit in the back. Like this is not a college lecture going on, right? So we are here to learn from you, and we want you to learn from us, right? So, yeah, come on. Okay, cool. So I was initially planning to split this into two parts. So first I would cover the theory of foundational models, and then I would cover like how do you actually go about training a foundational model, right? So, but like based on the interaction and the pulse check, I think let's cover theory in detail, right? And then we see if we have time left at the end of the session, we'll try to do a bit of practical, right? So what is a foundational model? Like that's the first thing, right? A foundational model is a type of machine learning model. That's a very generic model, right? Like if you have used ChatGPT, it's a generic model. It knows how to generate text, but it can also do maths for you. It can also do finance for you. It can also do like history lessons for you. So it's a generic model, a model that's generic, that's trained on vast amount of data. So if you have heard, like foundation models are trained on trillion and trillion number of tokens. Now tokens are basically words in case of text, but in case of geo, they mean images, right? In geospatial, it means images. And they're not trained on any specific task. So people here who work with machine learning, can you tell me like some of the problems that you deal with? Like like it might be a research problem, something that you're doing on the field, something that you're doing on your project. Can anyone give me a few examples of what machine learning projects they're working on? Anyone? Sorry? Reinforcement learning, what are you doing on reinforcement learning? Sorry, I can't hear you.
Recent research is on reinforcement learning related to machine learning models.
Okay. Oh, no, I'm asking like, what is it that you guys are working on? Let's say someone is doing flood detection, or someone is working on detecting earthquakes.
I'm doing on flood maps.
Flood maps, you're working on flood maps. Any other examples? Yeah? Groundwater?
Groundwater modeling.
Groundwater modeling. Okay, any other example? Can you give us a bit explanation of how you are doing it? How you are doing groundwater modeling?
Right now using traditional models, but
Okay.
I'm planning to inculcate ML into
Okay.
that.
Cool. And what data are you using for it?
Time series data.
Time series data sets. Okay. Any other examples of, yes, sir?
I've worked in multiple domains, like
Okay.
from floods to agriculture. I mean, one of the thing which I came to this conference is also for collaboration on building those kind of sovereign India-based. One of my presentation was on that India-based foundation models. So a key area is in agriculture. Especially for the global south. So that's something which I built a little bit, but I think it needs more work, right? For example, for what I've done is on cloud filling, build a foundation model, but use it for cloud filling and for other downstream applications, like for example, land cover. It has many other applications, right? Like from wildfire, I was also part of the AWS TGI challenge for wildfire prediction. But my keen interest is to see at some point, at least my vision is to see for some of these foundation models, time series based, not just vision time series pixel based or patch wise for agriculture in the global south. So like cropland estimation, yield estimation, land cover classification, and even like mapping of multiple crops and things like that. So.
Cool. Okay. So these are some of the examples that we just heard, right? So someone is working on flood mapping. Someone is interested in crop yield estimation. Someone is interested in groundwater monitoring, right? So these are like specific use cases that we as a community, we have been working on for decades now, right? So crop yield estimation is something that I was talking with like someone from ISRO, and his first project as a director was to do crop yield estimation, where he had tapes of data, carrying it, running around, and this was in 1980s, right? So these are like generic, these are not generic problems, these are specific problems that we as a community have been dealing with for some time. But there is no easy solution. So to do crop yield estimation, I need to collect a lot of data, I need to label them, I need to train a model, and that model is very specific. Let's say I do it only for Hyderabad, that model works in Hyderabad. I take it to Bangalore tomorrow, the model doesn't work in Bangalore, so I have to retrain it, and there's so on and so forth, right? That's what the field of machine learning was, and it was stuck in that era for a long, long time until foundational model came, right? So to give a brief idea of like how foundational model is useful, people here, anyone from Orissa? Anyone here from Orissa? Tara, yeah, but no one here, right? So I assume that no one knows Odia here. Odia is the language that people from Orissa speak, right? So I give you an easy task. Okay, I'll tell you a sentence in English. Okay, so it's a nice weather out today, so I'd probably like to go and play football. And then I'll tell you a sentence in Oriya, which is आज आम एठू आसीचु गोटे टक दवा पई वाइब चेक करिया पई हमकू टिके टाइम लागुछ now between these two sentences which is the one that you understand between English and Oriya? You understand English better than Oriya, right? Is that a common understanding because you don't know Oriya? Now like think of yourself as being model, right? So you are the machine learning model and you are given the task of giving positive or negative sentiments to these sentences. So because you know English, you can easily annotate data sets that are in English. But if you don't know Oriya, then maybe you look for some patterns. You look for some patterns in the sentence and you see, okay, if the word bhalo is there, then it means positive. If the word kharap is there, then it's negative, right? But as a model, it's easier for you to give good right examples for English sentences, but not for Oriya sentences because you don't know the language. So pre-2020, pre-GPT or pre-chat GPT, that's what people were doing, right? So the model has no understanding of language. The model doesn't understand English, Hindi, Oriya, Spanish, French, any language, right? But we are asking the model to solve specific tasks. And the task was text summarization, sentiment classification, question answering, right? So the model has no understanding of the language, but it was still trying to solve the problem for us. And what ChatGPT or GPT, the algorithm behind it, did is it solved the problem. It tried to teach the model language. So it tried to teach English to the model. It tried to teach Hindi to the model, Telugu to the model, Oriya to the model. And that's how the field of NLP evolved into something that we are seeing today. Like you are using ChatGPT for your assignments, for writing emails, for doing your finances, and so on and so forth. And that's what we want to take from text or from NLP, and we want to apply it in vision or the vision community. So this is what we are going to do. Like, we need to find that one trick that would help us to teach the model language of pixels. So GPT understands language of text. So text is the input to GPT model, while pixels are input to vision model. So we want to take the same paradigm that GPT solved and we want to apply it in vision. Okay. So that's what like a foundational model is. And today we'll talk about geo foundational model because it's IEEE, IGA, so specific to geo. So how is a geo foundational model different from any other foundational model, right? So one thing that we all understand because we are all from geo community is geospatial data is unique. So we have optical imagery, we have SAR imagery, we have LiDAR. In optical, we have 3-band, 11-band, we have multispectral. So there is different types of data that is out there. We also have time series. So any image that a satellite captures is not a spot in time, right? It's a time series. So you can look at the same place over and over and over again. So that is time component. And then the third thing is resolution. So if you're looking at Sentinel, so Sentinel is at 10-meter resolution versus we are looking at NEP, which is at 1-meter resolution versus we are looking at MODIS, that's 250-meter resolution. So the resolution of the imagery varies as well. And along with all of this, you have a lot of metadata. So you have weather information, you have clouds, you have location, and all these things that are just unique to geospatial. They're not generally there in your RGB imagery. So if I take a photograph today, that's an RGB image that has no coordinates, that has no multispectral bands, that has no time information. It's just an image. But geospatial data is special. So there's a lot of like things that build geospatial data special, and that's why we need to build a geo-specific foundation model, right? I'll take a pause here. Are there any questions so far that people have? And feel free to like stop me in between if you are in doubt for something. Any questions? And don't feel shy to ask questions. There are no right or wrong questions as such. Questions are always right. So are there any questions so far? Are you getting what I'm saying on foundational models? Do we do a pulse check, like hand raise on things that we are discussing? Do you understand what foundational model is? Why we need a geo foundational model? Anyone who is not able to follow? I'm not getting a yes or no. Maybe the biryani was too good, is it? Is it making everyone dull? Cool, okay, let's go ahead. So there are a lot of foundational models. Now, sir discussed about, yeah.
It's just a nuance, but I think you alluded to it as well, right? Like, how do you build generic models and then fine tune it for specific tasks, right? So, I mean, that's important. But even when your comparison regarding the language models in ChatGPT also, it's not like the model of ChatGPT learns about a language, right? I mean, most of it is like some kind of masking and trying to figure out. So it's a probabilistic based approach of kind of next word prediction, that kind of thing, right? And sentence. So it depends on the, like a lot on the how you train it and everything, but it's not like the model understands that, okay, I have learned this particular language. That's not what it is. Actually, it's just able to learn the structure of the phrase, the grammar and everything. So just also alluding to what you talked about is, it's more like trying to train the model to understand the type of data that's coming and in the format and everything. But even like, I mean, you also alluded to the fact that there was a lot of studies going on in yield and everything. It's not like foundation models are going to change all of that. We still need that because all of that knowledge and everything is very important, because how you provide the input data is still very critical for even when you're building a foundation model, Yep. So it's not like that's going to go away with this. So it's not like a magic wand. It's just that we are, I mean, it's definitely necessary because it helps you to kind of build a generic model, which is not like fine-tuned for specific tasks. But still, there's a lot of hard work that has to be done in even building that data set. So that actually we can get inspiration from the previous work, classical approaches that has been done. So I just want to add those two comments.
No, both are great points, and we'll cover a bit of it in the session. So data set and what data you pick to build models is fundamentally important to building foundational model. Like that's the difference between a GPT versus a like you can I'm not finding a good example here, but I basically have a T-shirt that says like data eats model for lunch, and that's how I describe it. Like how you design your data set is everything related to how good your model becomes. So I'm completely aligned with that. Yeah, so to continue, like we wrote a blog post last year comparing all the geo foundational models that were out there. There's a link to it in the slides. You can find it on the page as well. So we were looking at like multiple models. So there was Prithvi, there was Presto, SATME, ScaleME, DOFA, and Clay. And we actually built Clay. So we are the authors of Clay, and we helped build Prithvi. So we work with NASA and their team in building their foundational model, which is Prithvi. And SATME, ScaleME are other models that are out there. So Sir's point on time series model, Presto is a time series model. Google recently released Alpha Earth, which is a pixel-based model, which is along the same lines as Presto. So all of these models have like different number of parameters, different training techniques, different data sets that they have been trained on, different resolution they support, and different types of downstream tasks that they can solve. So this is a blog post that we wrote that we tried to cover and match. So that kind of helps you to pick and choose. So if you have a task at hand, you can go to the blog post, figure out which model is right for you and use it in your workflow. Again, coming back to the same thing, data. Now data is everything. If you want to build a model, even before when we were doing traditional machine learning, we had to create our data set, right? Like that was very important. In case of foundation model, data is as important as it was yesterday. So designing a good data pipeline is very, very important. I'll share my experience building Clay. So Clay was one of the best models that was there till last year. Today we have better models than Clay, but I'll cover like what it took for us to build a model like Clay and what the data pipeline was for Clay. So we wanted to cover data for the entire globe. So we just heard someone say, we want to build an India-specific foundational model. And that is because a lot of the models that are out there, they're trained on global data, and they don't cover India really well. So the data is mostly trained on European satellites or US satellites or regions covering US and Europe, and then you take it and apply it Southeast Asia, it doesn't work, right? Because it has not seen data enough for Southeast Asia to be able to adapt and learn. So one thing that was very important for us is to have a good global data coverage. So the image you see on the screen is, so all the yellow dots you're seeing is basically all the MGRS tiles that we took to train our model, okay? Then we designed a sampling strategy. Now, you don't want to oversample on a few things. So inherently, Earth has a lot of patterns. There are a lot of grasslands. There are a lot of agricultural lands. There's a lot of lakes, ocean, right? So there's not a lot of entropy in that data. What you want your machine learning model to learn is entropy. It wants to see a lot of diverse data than the same data again and again. So to do that, you design different sampling strategy. We use ESA's world cover maps to get land use land cover statistics for each MGRS tile. From that, we picked the tiles that had like good representation of all the classes, right? And then we over-represented human settlements because that's where you find most entropy and there's a lot of diversity in there. But then we had like a good enough representation of all the classes that is out there, and that helped us build a better, more generic model. Because we were training a foundational model, now I don't know if you guys know it, it takes a lot of compute to train one foundational model. To train Clay, it took us almost $1 million of compute on AWS. So it's very expensive to train, and to make sure that you're using your GPU really well, you need to have like a very efficient data pipeline. So we had to feed close to 5,000 images per second to the GPUs. So we had to design like a very efficient data pipeline for it. So the standards that Tara covered, which is TAG, COG, ZAR, is what we used. So we pre-created chips of data, created data cubes, stored it in the most efficient data store that is out there, and use it to feed our model. Altogether, we trained it on 70 million chips. So if you are like doing a normal ML training in geospatial, you'd have
I
like,
just have one
Yeah.
point. You know, I'm just trying to make this more
Yes.
interactive.
Yeah,
If you don't mind.
yeah, no worries. Yeah, love the questions.
I would just suggest, I mean, I really I followed Clay, the work of Clay for quite a bit of time. And, you know, right now there's a lot of discussion going on Clay versus the Alpha Earth, you know, the embeddings and all of that, you know, so interesting discussions. You know, like, so that's what my main point of saying that Global South needs a separate model is because if you look at your previous point, right, like you're using samples from ESA's world cover map, you know, I would debate that. For example, the ESA's world cover map is particularly bad for the Global South. You know, it works fantastically well for the European region, but it's particularly bad in Africa and India and other places. So when you're relying on that for sampling, obviously you will be biased.
No, that's a great point. And
Because like if you're saying like, let's say the human settlements, I think it works very well. You know, like there's no debate about that. Urban areas, you know, like water bodies, they all work very well. But if you're looking at croplands, grasslands, shrubs, trees, you know, like all of these are, which are very necessary for agriculture, deforestation studies, you know, like the biodiversity that we have, you know, is humongous that only for each of these countries alone, you need one foundation model because there's so much of diversity. And for that, like, and you're absolutely right. I think the pipeline is right, is that you would have to take a world cover, then do a sampling. But the problem is that the world cover map itself is wrong, you know, then your sampling strategy is hit. Your sampling strategy is good, but the problem is that the fundamental baseline map itself is wrong.
Yep.
You know, and that's where I have a big problem with many of these foundation models.
Yeah.
And hence my original thing that to become a sovereign nation ourselves, we have to build our own our own land cover maps and our foundation models.
Yeah, no, I agree with everything you said. And I understand ESA's world cover maps are biased towards Southeast Asian nations. And yeah, we should do better sampling. And that's something that we encourage. And the multiple communities that we are part of, where we are trying to drive that to bring more diversity in the data that they train on. The only thing that I would disagree is we need our own foundational model, but we can debate over it like during the session, we can cover it. So that kind of defeats the purpose of like what a
I'll
foundational model.
tell you why I explain that, because I've seen many foundation models when they're doing generically trained, you know, like because you have a limit, maybe the future foundation models would be able to take care of it. But right now there is a humongous amount of this saturation. There is only so much of entropy and variance that you can actually build into your foundation model. If there is very high entropy in a particular area, local area, then it becomes problematic, you know?
Yeah, no, I completely agree.
That's why like it's very specific.
Yeah. No, I agree with that. And then I think, so what I am aiming for is the future where a generic foundation model is able to do as well in Southeast Asia versus like how it's doing in the West, right? So that's the future that I am aiming for. But yeah, we can have a discussion around it. Yeah, so this is about the data pipeline. Now let's cover the model design, right? Like what a foundational model looks like, right? So generally we need a task, a generic task for us to train a foundational model. And can anyone tell me why? Like what's the limitation with a normal ML model? Like for example, someone is doing flood mapping, right? So to do flood mapping, what do you need in terms of data?
In terms of data, I am using diff checker software, sir. In that we subtract images and we find out the final image. And we plot out where that image is there.
Okay.
In rough terms, I am telling, still work is going on, sir. I am not able to recollect properly.
Yeah.
And some more softwares are also there, sir.
Cool. And how much time?
Particularly, I am working on diff checkers.
Okay, but how much time does it take to create those data sets?
Time based on the capturing capacity of the satellite to capture the flood areas.
Okay, so it's limitation on the satellite side, not on the effort required.
And limited to area where the floods are.
Okay, cool. The general bottleneck in any ML model or pipeline is the data set, So if I am doing crop yield estimation, I need a lot of good data that can accurately represent what crop yield is in the area of interest, right? And how do we get good data? We have to send scientists, people on the ground, collect data, do manual annotation, and that's not scalable. So that's scalable to an extent. Like I can do it for my city or my state, right? But you can't do it at a world scale. And to build a model at world scale, you need data that's world scale. But no data is, so it's impossible to create human annotated data at world scale. So we can't do it. That's why we have to think of an auxiliary task, right? Like a task that's pseudo, that's not related to our problem, but also is relevant for the model to learn some patterns. And that's what we call self-supervised learning is, where the model learns from the data without human supervision or without human annotated data set. There are different types of SSL learning. One is called contrastive learning. So if you have, you will sit down, sir, like you don't understand. Yeah, yeah. So the different types of self-supervised learning. There are basically two families. In case of vision, there is contrastive learning and there is masked autoencoders. Papers like SimClear, Boyle, and Dino are based on contrastive learning. So to simplify what contrastive learning is, you basically take two images. Let's say you take an image of a dog here in the slides, an image of a chair, and you augment both, right? So you change the image by adding rotation, change color, do some changes to the image. You pass it through the network, and then images that are coming from the same source, right? You try to move the embedding space closer. And images which are coming from a different source, you try to push the embedding space apart. So that's what like contrastive learning is. Like that's the auxiliary task for contrastive learning. You take two different images and you do augmentations. You move the embeddings closer for similar images and you move them apart for dissimilar images. Clip is a style of contrastive learning which combines images with text, right? So if you have seen like today, like models like ChatGPT can interpret images, can interpret text, can do image summarization. That's because they are trained using a clip style of model, where image is an input, text is another modality that goes an input, and images that are representative of the text, they are moved closer together, and that are not, they are moved apart. MAE is the second technique that people generally use to train foundational models. In MAE, what you do is you take an image and you split it into patches, right? So you'll take an image, here you see like there's an image of a, I don't know what that is. That's a pigeon, orange color pigeon or something. But what you do is you remove 75% of the pixels from the image, right? So you take an image, you remove 75% of it, you pass it through the model, and your auxiliary task is to reconstruct the image back, right? So you take any image, you remove 75% of it, pass it through the model, and the task for the model is to reconstruct the image back. And that's the auxiliary task that the model learns during the process. So here are a few examples. So the first column is the input to the model. The second column is what the model predicts after training, right? So you can see it can easily, like, I don't know if a human can do this, but the model from the first column is able to like almost like 90% able to reconstruct the leopard, the desk, the waterfall, and the dog, right? So that's the task that the model is trained on. So this is the architecture of Prithvi. It is a very similar architecture. You take input as images, but Prithvi takes time series as input. It adds location information, which is specific to geo. It passes it through the encoder and the decoder and tries to reconstruct it back. I'll not go into too much detail of this. Like if people want to, let me know, I can dive deeper. This is the architecture of Clay. Clay is very similar, but it uses something called a dynamic encoding block that allows you to support different types of satellites. So Prithvi can only handle HLS data, so Sentinel and Landsat, but Clay can handle Sentinel, Landsat, NAPE, Planet, MODIS, LINS, and everything in between. So it's the dynamic embedding block that enables Clay to do this. Apart from that, like Clay and Prithvi are more or less similar architecture. To train a foundational model, you need a lot of compute. So we trained it on 384 GPUs over 2 months to be able to reach to a stage where it could do like reasonable tasks, but it's an expensive process. I'll skip DDP, FSDP for now. Yeah, let's go into embeddings, right? So, can anyone here explain like what is your idea of embeddings? Do you know what embeddings are? Sorry, clipping. Keeping something inside? Yeah. No, that's not the right embedding. That's a type of embedding, but that's not the embedding we are discussing here. Anyone else here wants to try what embeddings are? Yeah, I'll give someone else a chance. Anyone on the back? Like, do you want to explain what embeddings are? Do you understand what embeddings are? Nope. Okay. So when you have a model, you pass an input through the model. Oh, you want to give it a try? Yeah. You want to take the mic? Where is the mic? Just a second.
It's like mixing of some like text embedding. You need to mix those things and you need to produce that output.
But what is a text embedding?
One part of text and another part of text. You need to give that whole output.
Yeah, let's try to like deconstruct it, right? So there is one text, right? There's another text.
Yeah.
But where is embedding in here? There are texts, right? How do you go to embedding from text?
Combining means
So let's say we take two sentences, right?
Okay.
There's a dog and someone is swimming, right? I can combine this as there's a dog and someone is swimming. Where do we get embeddings here? No, yeah, cool. No worries. Yeah. Anyone else who want to give a try at what embedding is? Sure, yeah. Let's hear that. Yeah. Can we have the mic here, ma'am?
I have to take off, so I promise I won't bother you anymore. This is the last one.
worries.
I would consider embeddings as a representation. Okay, obviously it's a numeric representation. It's a compressed representation, right? So the original philosophy of embedding is how do you find the best representation of any kind of modality of data set that you have, whether it might be images or text, that is best representative of that, but in a really compressed format. So you might have many kinds of data, there might be redundancy in it, but how do I represent that in a minimal format, in a compressed format, all of that data, which will be either, it can be from a statistical perspective or it can be from a world universe perspective. It's very similar to how human brains work, right? The idea is that how do we embed the world information that we have in a compressed format, right?
Yeah. No, that's. I think I can do a better job at explaining embeddings. That's
Maybe
what
you can.
embeddings are, right? It's basically compressing your input into a format and that's small enough to be stored, but it has enough information to reconstruct your input back. Okay, so that's what embeddings are. So embeddings kind of capture semantic meaning. That's the whole point. So if you take an image, you pass it through a model, you get some numbers out, but those numbers are representative of the image. Okay, so they capture the image as a whole. This is a nice animation of what embeddings look like. So you see here, we split the entire California into patches. We take those patches, pass it through the model, get embeddings, then we do a PCA on embeddings, and then we project them back into the space. And now you can see it does land use land cover classification by default. Like you don't have to do anything. I'll replay it for others to look at, right? So, oops. Yeah, you can see here, it takes images, splits into patches, passes it through the model, gets the embedding, and then tries to like do PC on it, assign color, and then moves them back. That's what embeddings are, right? Like they contain semantic meaning. let's, let's look at embeddings again. Now, this is an example of what embeddings look like. On the left, you see there's an image. It's an image of a beach, okay? And on the right, you see a lot of small cubes. Each cube is an embedding. Now you see like there's some cubes which are very well represented. Now, if you look at this image, so this is land and this is water, and there's a lot of embeddings. One particular embedding, this is embedding number 97. It can do a land versus ocean classification out of the box. Like it's not trained to do land versus ocean, but it can do it out of the box. There's one here which detects underwater. People do like coastline, like degradation and stuff, right? Like so, the embedding number 102 kind of does that for free. And then there are embeddings like this, which doesn't make any sense, okay? But it doesn't make sense to us, to humans, right? But for the model, every embedding there, it has some meaning that it attaches to, okay? And when you use those embeddings in your downstream task, they're really, really useful. Here is another example. So there we were looking at one image. So for one image, we're looking at all the embeddings. What I've done here is like I've taken multiple images. So the first rows are the images. The second rows are one embedding, embedding number 97, which was doing like a very good segmentation. So you can see here, like you get segmentation for free. So when you train a foundational model and you look at one vector out of it, it kind of does segmentation for free. So here you can see when trees from grassland, it is able to separate ocean from land and many other things, right? And we didn't train our model for any of these tasks. The model was trained to solve a Sudoku puzzle, which is take 25% of the image and reconstruct 100% of it back. It was not trained to do segmentation. It was not trained to do classification. It was not trained to do detection, right? It was a generic model. And it was able to learn all these things in the process. Here are more examples for the same. So what are some of the downstream tasks we can do once we have a model like this? One easy task that you can do is once you have a model, you can take any region of the world, pass it through the model and get embedding vector. And that's what we did. We generated embedding vector for the entire US over multiple period of time. And then what we did is for Claremont fire that happened in 2023, we took images from the year 2022 and images from the year 2023. We passed both the images through the model, got two different embedding vectors, and then we did a diff of it. So embedding for images before the fire, embedding for images after the fire. So when you do a differentiation of that, the vector that you get is your wildfire detection. So you take the diff and then you do a search over entire US and it can detect all the events that ever happened in US for wildfire. It takes 5 minutes to do this. Like you don't really need to build a model to be able to like do this at good enough accuracy. You have the embeddings, you have the model, you just use it to do wildfire detection. You can do PCA on embedding. So you have embedding vectors that are generally 1,000 to 2,000 numbers long. You can do a PCA, reduce it down to 2 or 3, and then try to plot it. So here you see like for the same region, this is a region in Portugal. We took images over different period of time and we plotted it. And here you can see like there are two green dots which are standing apart. They are cloudy images. So you can easily do cloud filter. So if you have, let's say, 1 million images and you want to do cloud detection, you just do a PCA and you can do cloud filter for free. And then all the blue dots are the events before a fire and red dots are the event after a fire. In the image on the right, it's not very evident, but on the scale that we are dealing with, it's very easily separable. So you can train a linear classifier to do this for you. You can do tasks like semantic segmentation. For normal ML model training, it takes a lot of data, it takes a lot of compute, and you need a lot of expertise to be able to do this. But with a foundational model, you can spend like 10 minutes on 1,000 images. You don't need a lot of labels. You can do it on 100 images as well. And you get as good a model as like a state of the art or like whatever the best is in your field, you are able to do it. Similarly, we did regression. Now, this was a challenge that was hosted on Driven Data, and the top scorer was around 0.27 or something. With Clay, we were able to train it for like 20 minutes on 5% of the data, and we were in the top 10 of the solution. And this was a paid competition, so there were like some 1,000 odd entries, and with Clay, with 20 minutes and one single GPU, we were able to like get like top 10 score with the model. You can do like classification, detection, and all the other like traditional tasks that you do with a foundational model. But it just makes your work easier. It makes your work faster and more accurate in those situations. So that was all 2024. Models have changed in 2025. We'll cover like what foundational model looks like in 2025. So this is a paper that got released earlier this year, which is combining text with images. So you can select an image, then you ask it like, what disaster has occurred in this area, and it can tell you if there's an earthquake, if it was a flood, if it was a cyclone, and so on and so forth. So you can select a region on an image and ask like, what's the area of this building? It will be able to calculate it and give it to you. We are also like driving a lot of innovation along the data side, like Sir discussed. Data is one of the key elements in machine learning. It's also one of the foundational elements in foundational model training, right? So you need a lot of good data that's diverse enough, that covers the entire globe, is representative of the global south, the west, and the north. So there is Pangea. It's a forum that we kind of support. Copernicus Bench is something that is also coming up, which has like a lot of diverse data set for model to train on. So these are like some of the data sets that you want to use if you want to train a foundational model. Also lately, like we have been combining language models with foundational models. So this is a work that Tara did in his free time. It's called Geodini. So you can ask it, okay, London, but not in UK and Canada, and it will be able to like search for London in Canada and give it to you. You can ask for Hyderabad. It will give you Hyderabad maybe in India or in Pakistan, but you can ask it Hyderabad only in India, and it will be able to give it to you. You can ask for things like, okay, give me boundary of river Ganga, but add a 2-meter buffer over it. So these are the tasks that are possible now, combining LLMs and like this is not using foundational model, but like application of LLM. Similarly, we discussed Stack today. So you can use natural language query with Stack. So let's say you want, you're doing some research on floods that happened in Hyderabad last year. You can say, okay, go and find me sentinel imagery for Hyderabad in this region, in this time frame, and filter it by 20% cloud cover. And it will be able to like pull in all the data for you and have it in your disk, and then you are ready to do analysis. This is a product that is launching today. So even before it's launching, I'll give you a quick preview. So here, so it's called Zeno. It's called Global Nature Watch. Actually now, Zeno was previous name. So here the query is, okay, I want to find disturbance in Odemira. Odemira is a place in Lisbon. And it goes and it finds all these disturbances that happened. And you can see there's a cluster of large disturbances. It says, okay, it looks like there's a wildfire in here. Do you want to look at the satellite imagery for this place? And it goes and pulls satellite imagery of that place for that particular time range. I'll play it again. So it asks for disturbance alerts in Odemira. It goes and it finds Odemira where it is, pulls all the disturbances. And then you say, okay, give me satellite imagery for that place in August. And it's able to pull satellite imagery of the place. And you can see here wildfire like clearly visible in this area, and like make some like report or things like that. There's another work that we did with Google. It's called GeoReason. It was like one of the most talked blog posts. So here the user is asking, give me the most recent off-Nadir imagery of Hillsborough County after Hurricane Milton made an impact. And the model, both the foundational model and the LLM, are able to go figure out when Hurricane Milton happened, pulled in weather data, like where the tsunami was, where it made a landfall, figure out that location, and then pull imagery for that. Then the next query is, okay, how many buildings were damaged in here? So it's also able to pull building footprints data, then do a delta of all the buildings that are before and after, and give you like a rough estimate of how many buildings that were damaged in that area. And the third query was, yeah. Sorry? Yeah, you can do all these type of queries with this, right? Like this was a prototype, but what we are building is to enable that, right? Like give basically democratize geospatial, like people with no or less geospatial knowledge can come in and start doing analysis like this for like for free. Yeah, so that's mostly it. That's what I wanted to cover. I'm happy to answer any questions. We have still 10 minutes left. I wanted to cover like how do you fine tune a foundational model, but I don't think we have enough time. Like 10 minutes is not sufficient. And then also like based on the pulse check, it doesn't like that's the best use of our time. But I'm happy to help like answer any queries that people might have about everything that we discussed. Anything in general about machine learning or geospatial or foundational models. Yeah, we still have 9 minutes left. So. And this is like my and Tara's email ID. If you ever need something, ever have any queries, want to chat, like feel free to email us. We'll be more than happy to like talk with you guys. Any questions on what we discussed? Still have 9 minutes left, so I can give you a 9 minutes back if you have no questions. Yeah. I'm not able to hear you. Yeah. Okay. So it's a very yeah. So the query is like the QGIS software that you're using is not getting updated regularly. What is the reason behind it? Yeah, I'm not the right person to answer that, but Tara maybe because he was at a QGIS conference lately. He was giving a talk. Do you know why? No?
Not the release cycle, sir. When we work on it at later times, it is not coming, sir. Again, we can't go back to the previous one. It is compatible, sir. First, we have downloaded one software. When we are again trying to work out after 6 months, it is not. After 1 or 2 months, it is not coming, sir. Like that. It's not. It's not loading.
Yeah.
First, we have downloaded the QGIS software. When again after 2 months, when I am trying to use it, that may be a different case. But at first, when we downloaded, again when we try to use it, it is not coming, sir. That may work.
I know a few other labs working on it. So applying LLMs to geo is one side of research that's happening. Building foundational model, application of foundational model is the second thing that we're seeing. That's going to continue for the next couple of years, I'd say.
Do you think applying LLM to Geo AI is needed in this time, or we don't, or we could do as usual as it is?
Applying LLM to geo AI,
Applying LLMs means we are in AI race right now. We are in means using AI models and optimizing everything. So is it necessary, or means in what sense are we applying?
how are we applying LLMs to geo models?
Yeah.
Right. That's a good question, right? So there's an independent application, like for example, like the example that I just showed you about WRI. So this one, if you see here, so here there is no GeoFM, right? So it's all driven by LLMs. So you can ask a query, I'm asking about disturbance alerts and for the Mira, it's natural language. It gets translated into a stack query. It pulls in data from the query, plots it on the map, right? And then I ask, okay, can you pull satellite imagery for me? So it's using geospatial tooling, like the stack tools, the cogs, the ZARs internally, but it's not using any foundational model in here. It's just LLM driving the interface and driving the user interaction. So that's one part of what's happening. The other part is the Google project that I just discussed here. So here you see like it's actually able to pull, it's actually running a weather model in the background to figure out like where did Hurricane Milton do landfall. And it took that point as its point of reference. And then when you say, okay, I want to do a building damage assessment, we are not using a model for this, but you can use a model. So you have an area, you have satellite imagery of the place. Then you can say, okay, I want to do a building damage assessment of it. You take before after image, pass it through the LLM, you pass it through the GeoFM. GeoFM does like a building delta and comes back to you with the results. So you can combine both as well, or you can use LLMs independently.
Thank you.
Cool. So we have 2 more minutes left. I'm happy to answer anything, but yeah. Yes.
Hello. Sir, we are working like during flood minus before flood. Sir, what would be your suggestion, sir? Before flood minus during flood, or during flood minus before floods?
Oh, I don't have much say on that. I'm not a GIS person. Like I work on the model. I
Normal
understand
analysis.
GIS data.
No.
But
It is not GIS data, sir. If
Yeah,
we
yeah.
consider normal data also, we are doing during flood minus before flood. What would you suggest?
I think it depends a lot on the type of model you're using, right? So if you're using, let's say a model takes time series as input, it takes before and after and does like you would have seen change detection models, right? So it takes both before after image and does a change. So that those models are more useful rather than you doing manually. If you manually do a delta of this, the results you'd get would be less accurate than like passing both into a model that's trained for tasks like that can do a change estimation.
So nothing wrong if we do during flood minus before.
I don't think so, but I don't think you should do that. I think like you use a model that can understand both at the same time. Yeah, so we are almost at time. Thank you so much for listening through, and yeah, thank you in general. Bye bye.
Thank you so much, Mr. Soumya and Mr. Tarshish. Now I invite Mosme ma'am onto the dais to felicitate our speakers today. I request Mr. Soumya and Tarshish to please come onto the dais.
Vijender sir, please. I would like to inform that today's tutorial was totally funded by GRSS Industry Relations Committee, and they have funded not only their travels, their accommodation, everything, whatever is being supported by Development Seed is funded by IEEE GRSS Industrial Relations Committee. On the top of it, thank you so much for sharing your knowledge, as Development Seed is the knowledge partner for EarthSense, and the content what they have delivered. Last time we have listened the same content in INGAR's 2024. That was the inspiration to bring them here. So it is always a kind of chain. If either of us, if we like the content in one conference, we definitely would like to pull the same content in our event, in our college event or in our university events. So that is the same flow we are bringing here. Thank you so much, both of you, and it will be always a pleasure to have you.
Thank you, ma'am. Yeah. More forward or thoda. हाँ वो लाइट गिरा. Yeah, now it's okay.